an eigenvalues and eigenvector, and how to find eigenvalues when we have distinct roots, eigenvalues and distinct vectors and repeated roots. We know how to find eigenvectors. Now we shall go for properties. Properties of eigenvalues. Okay, right? So, what is an eigenvalue? How we are getting? From the characteristic equation, a minus lambda is equal to 0. Right? A minus lambda is equal to 0. Right? This I is an identity matrix. Right? Okay. So, I have something minus lambda, something minus lambda, something minus lambda, and so on. And I am having some values here. Okay. What happens when I transpose this matrix? What happens when I transpose this matrix? This diagonal will not change. Right? So, what is the first property? A matrix A and its transpose, right, have same eigen values. Okay, this is the first property. This is the first property, right? Okay. Second property, sum of eigenvalues. Sum of eigenvalues is equal to the trace, equal to the trace of given matrix. Given matrix. Right? What is trace? What is trace? Sum of diagonal. Sum of diagonal, leading diagonal values or elements. Right? Sum of eigenvalues. If you add, right, all the eigenvalues, then the sum will be equal to the trace. The trace. Okay, what we have. Previously we did one problem. 2, 2, A. You can check. Right? There. What is there? Trace. Check the trace of the previous matrix, whether it is 12 or not. Okay, it is 12. That is why when we form the formula lambda cube minus S1 lambda square, that S1 is right. Okay, right? You know the theory of equation. When you have an equation ax square, x square plus ax plus b is equal to 0. What is this a? Sum of the roots. A is sum of the roots. Sum of the roots. B is product of the roots. Minus product of the roots. Right? When you have x cube plus ax square plus bx plus c, this is sum of the roots taken one at a time. Sum of the roots taken two at a time. Sum of the roots taken three at a time. That is product of the roots. Product of the roots. Based on this principle, we have formed the formula. Okay. So sum of the eigenvalues is equal to the trace of the given matrix A. Here it is A. Okay. Third one. Product of eigenvalues. Product of eigenvalues is equal to the determinant of A. right? So product of the eigenvalues is equal to the determinant value of the matrix. You say the previous problem we have 8 to 2, 8 into 2, 16 into 2, 32. 32 will be the product. Okay. There you are having lambda cube minus 12 lambda square, minus 12 lambda square plus 36 lambda square, 36 lambda minus 32 is equal to 0. Right? So this 32. Right? Okay. Right? Product of eigenvalues is equal to the determinant of A. Determinant of A. Right? Fourth problem. Fourth property. If lambda 1, lambda 2, lambda 3, are eigen values of A, then number 1, right? Number 1, k lambda 1, k lambda 2, k lambda 3 will be eigen values of Ka, will be eigen values of Ka. Right? Matrix is multiplied by a constant K. A constant K. Okay. Right? Any multiplication. If I want to find eigen values of 2A, then it is 2 lambda 1, 2 lambda 2, 2 lambda. Okay. Number 1. Number 2. Lambda 1 square, lambda 2 square, lambda 3 square will be eigen values of A square. Right? Lambda 1 square, lambda 2 square, lambda 3 square will be eigen values of A square. A power n, lambda power n, right? Lambda power 1 power n, lambda 2 power m, lambda 3 power m will be eigen values of A power m. Okay, right? One by lambda 1, 1 by lambda 2, 1 by lambda 3 will be eigen values of A inverse. 1 by A. 1 by A is A inverse. Right? So using this, you can do all. You can find the eigen values of all matrices. Multiplication of matrix, power of matrix, and so on. Right? Okay. If lambda 1, lambda 2, lambda 3, right, are distinct eigen values. Distinct eigen values. It is that lambda 1 not equal to lambda 2 not equal to lambda 3 are distinct eigen values, then the eigen vectors are linearly independent. Eigenvectors are linearly independent. What is linearly independent? You can form a combination, right? You can form a combination of vectors, right? x1, x2, x3 are eigenvectors. then we have a relation k1 x1 plus k2 x2 plus k3 x3 is equal to 0. The linear combination of the vectors is equal to 0. We say it is linearly independent. If they are not distinct, then they may not be linearly independent. They may not be linearly independent. So for repeated values, we are finding linearly independent vectors. Right? For transformation, for linear transformation, orthogonal transformation, whatever it is, the eigenvectors are very important. We are going to transform the matrix into orthogonal form or normal form or any other form. We need linearly independent vectors. So it is very essential to find linearly independent vectors. Right? If they are distinct values, then not essential. This is property of eigenvector. Eigenvector. Right? Property of eigenvector. Right? Okay. Right? These are the properties. Please take down the property. Now we can pause. And then we can